Hi everybody, in the last video we talked about the dependent samples T equation. It's different from the independent samples T equation because it's a different situation. Now in this video we're going to actually apply it and we're going to see how to solve a problem using the equation. So I'll give you some data here and a scenario. We'll see how this all works out. We'll interpret it in a future video, however, but at this point you can see how we arrive at the T value. Now, all of these data are made up in this situation. This is an entirely fictional scenario, but you can see how the data work out. For this little scenario, let's imagine that we want to test out a smoking cessation intervention. Let's say that we're going to hypnotize people for about 30 minutes. Now, of course, you could quibble with me about how long the intervention is taking, sort of the amount of intervention that people are receiving, and all sorts of other things in here. There are a lot of questions left here. That's all fine and good. Let's just imagine for the moment that I've kind of dealt with all of that, and we're going to focus on the statistics here. So one way that we could do this is we're going to recruit people. We're going to see how much they smoke, deliver the intervention, and then see how much they smoke after the intervention and compare the two time periods. So this is a dependent samples design because the people in group 2 definitely depend on the people in group 1 because it's actually literally the same people. Okay, that's called a repeated measures design. In this particular case, we're going to measure their smoking at time 1, then measure their smoking at time 2 after we introduce this intervention. So let's just say that we have 8 people and we ask them how much they smoked in the last 24 hours essentially. Then we introduce our intervention, which is the hypnosis session for, we'll say, 30 minutes. And then I ask them 7 days after this, how many cigarettes did you smoke in the last 24 hours? Okay. Now again, you could argue with me about all sorts of these details. That's fine. Just accept them for the sake of this particular example. Now, of course, our null hypothesis, our default assumption, is that our intervention is going to make no difference whatsoever, right? There's no relationship between the independent variable and the dependent variable. And so therefore, we should see no difference in smoking from time 1 to time 2, because it's as if we weren't even there. There was absolutely nothing going on. So we would expect a mean difference, which is what these symbols mean, of 0, mean difference of 0. That's our default hypothesis. Now the alternative in this case, we're going to make this a one-tailed test in that we're going to specify the direction of the difference we're going to see. Because we're trying to reduce smoking, we're going to ignore the possibility that our hypnosis is increasing smoking. That seems probably safe to do it at this point. Or at least if we are increasing smoking, we want to find a null result and find out that we shouldn't be using this intervention at all anyway. Okay, so of course, what would happen then is if we are reducing smoking, we will have a bigger number of cigarettes at time 1 than time 2. Therefore, we would end up with a net positive difference. Okay, we would have more cigarettes smoked at time 1 minus fewer cigarettes smoked at time 2, therefore a positive difference. Now, we need to see which one is more accurate. More accurate, or perhaps I should say more supported by the evidence. So let's do that. Let's say that this is our data set, okay? As I said, I had 8 people recruited, and in this particular case, there wasn't a second group of 8 people. It's the same people in both groups. It's very important, therefore, that I keep track of these people. Person 1 was person 1 at time 1 and person 1 at time 2. Okay, I can't mix these up. In an independent samples t-test, it doesn't matter. The rows don't really matter. You can just mix all those up as long as they stay in the same columns. But in a dependent samples test, it definitely matters which row they are in, as we will see very shortly. Okay, so this is how many cigarettes each person smoked at time 1. In other words, person 4, participant 4, smoked 4 cigarettes in the last 24 hours at the first time that I asked. We did the intervention, and then that same person smoked 2 cigarettes within 24 hours of after the intervention, right? And that's how all of this works. Now, here's the equation as I introduced in the last video. And here is everything that we're going to need here. So very quickly, again, we're going to need the sum of the difference scores, and we'll calculate those in the next slide. This is the mean difference that was stated in the null hypothesis. This is the, again, sum of the different scores except squared. In other words, we're going to square each different score, then sum them up. And of course, the little n means the total number of times that I have a difference score, okay? So let's do all this on the next slide. Here's where we've got that, okay? It's the same information here. So these are the same participants. These are the number of cigarettes they smoked at time 1, time 2. Now the first thing we need to do is calculate a difference score. That's very simple. All we do is take time 1 minus time 2. 3 minus 1 is 2. I do that's the same thing for participant 2. 5 minus 2 is 3. Same thing for participant 3. 2 minus 3 is -1. Now, note here, this person had smoked 2 cigarettes in the previous 24 hours before the intervention, but they smoked 3 cigarettes after that. So it appears it maybe didn't help this person. Anyway, you could argue, was that an average day though, however, or maybe that was a light day for them anyway, maybe this was a heavy day. All that is fine. A little beyond what we're doing here, however. So anyway, I just do this and I calculate these different scores for every single participant. Then what I do is I square that difference. You'll recall that the equation said we are going to need to square each difference and then sum up those squares. So I square each difference. 2 squared is 4, 3 squared is 9, -1 squared is +1, and so on. So I've squared all of those. Now I also need to get the sums. So I'm going to put in this bottom row to give me the sums. Now I need the total number of participants, or the total number of participants I had a measure for both time 1 and time 2, and that was 8. I had 8 different scores essentially. I don't need the sum of the group 1 variable, and I don't need the sum of the group 2 variable. I just don't need it, so I'm not going to bother calculating that. I do need the sum of the different scores. In other words, I'm going to add all those up, including the -1, which takes away from the total, right? That's fine. That's all built into the equation. For a total of 11, you can do the math if you don't believe me, and I sum up all the squares. So 9 plus 4 plus 0 plus 0 plus 4 and so on is 31. Now we're going to plug all of that into our equation. So if I just take that bottom row and keep it up here for reference, you can see how I'm going to plug all of these into the equation. Here's the equation, right? So first I'll need the sum of the different scores, which is right here, sigma difference, sigma difference. So 11 is going to go right there. I had a total of 8 different scores, that's fine, or 8 participants for whom I had measurements from both time 1 and time 2. This I got from the null hypothesis. The null hypothesis was I expected a mean difference of 0. By the way, maybe I'll explain that really quickly. Shouldn't this always be 0? In some cases it won't be 0, but in virtually every case it will be. So the only scenario where it might not be 0 is let's say you've got a weight loss pill that says we guarantee that you will lose at least 30 pounds. Okay, so if that could be my default hypothesis, and maybe I want to see if it's different from that. So in that case, I could set up the null hypothesis as 30, right? They're suggesting that it is 30, and maybe I want to make the null hypothesis 30, and I want to see if I can lose even more than that, or perhaps even less than that. Right? So there would be reasons that you might want to make it not 0, but in virtually every case it would be 0. So don't worry about that. Okay, so down here of course is the squared difference values, which is 31. So 31 is going to go right there, and then of course n sub d is always going to be 8. So if I plug all of those values in, I get right here. Again, 11 goes right there, 8 goes right there because that's what n sub d is. 0 goes right there, as I said. 11 also goes here as sigma d, and n sub d is always 8, right? So if I plug in all of these values, that's what I get. The only place where 31 goes, of course, is where the difference values are squared, then summed. So I'm going to put this on the next slide, and we will start to simplify the equation. Here we go. So here is the equation. Now, let's take a quick look at what we need to do first. Now, you always start in parentheses, and then within those parentheses, you follow the order of operations, which of course is the exponents first. And in this case, the only exponent that we have inside here, well, of course, we'll have the square root operator, but it's sort of implied that there are parentheses within the square root operator, so we have to work within that. So the first thing we do is we square 11 down here, right? And up here, there's nothing to do except to divide 11 by 8. Okay, so let's go ahead and do that. If we divide 11 by 8 and then subtract 0, we get 1.375. You can do that on your calculator just to follow along. And as I said, the only thing we can do over here is square 11 to get 121. Now we can also subtract 1 from 8. That's no problem because it's not going to affect anything else. So that's fine. I'll make that 7. And we can't do anything with 8 yet. So now I'll move this section over to the next slide. You can see the next thing we do. Once again, can't do anything on the numerator. That's already done. What I can do next is I can divide 121 by 8. So I'll do that. 121 divided by 8 is, of course, 15.125. Now, nothing I can do here. One quick note, however, is that this number has to be smaller than this number. Regardless of everything else, you will find that this definitely has to be smaller than this number. If you got a bigger number here, then there you did something wrong and you need to go back and figure out what it was. Okay, so at this point, all I can do is find the difference between those two. We'll do that on the next slide. There that is. And here's the difference. Of course, 31 minus 15.125 is 15.875. Now, of course, all I do here is divide that by 7. I'll do that here. Okay, 15.875 divided by 7 is 2.2679. Now, once again, I just need to divide this by 8. I'll do that on the next slide. Here's that. Once I've divided by 8, I get 0.2835, and then it goes on for a while, actually. I'm fine rounding just to these 4 decimal places, that's fine. So then I need to take the square root of 0.2835, which is, of course, 0.5324. Now all I have to do is divide 1.375 by 0.5324, which is, of course, 2.582. So that is our t-value. Now at this point, the t-value doesn't make a whole lot of sense. You'll recall what we need to do next is find out the critical value to then interpret and find out, is this statistically significant or not? And that is what we will do in our next video. I'll see you then.